Hi, I'm Jeff. I'm going to be talking about linear algebra. So this talk is going to be sort of a condensed version of a class that used to be offered here at Tech called Abstract Vector Space, which used this textbook, Tom Apostle's Linear Algebra. It's a very good book for just learning more advanced linear algebra than was typically taught in your intro sequence. I'm also going to expand a little more beyond linear algebra and also include some basic set theory. So with that, I will get started. So I'm going to start from first principles just so that people who haven't taken a set theory course before can understand where I'm going. But I mean, I shouldn't spend too long with first principles, so for the people that do have experience with it, it shouldn't be a problem. So a set is just a collection of objects, like, so it could be like a set of functions or a set of points. They don't even have to be the same type, so I could have a set that's like x, 2x, g of x, and yeah, so you don't have to have the same type of objects in a set, it's just a set of objects. They don't even have to be mathematical objects. It could be like a set of dice or the set of things I have in my left pocket. So a set is just a collection of things. An important tool when talking about sets are bijections. Bijections work like this. If I have a set that has A, B, C, or let's assume I have one set with 3 objects and another set with 3 objects. I guess 1, 2, 3. A bijection is a pairing, which will allow me to uniquely pair off the elements such that every element in one set has a unique pair in the other set. No one element is paired to 2 elements in the other set, and if I have repetition in the set, which I'm allowed to do, it's still paired with the same object. So like this would be a valid set A, B, C, A, because you're allowed to have repetition in the set.
A is paired with 2.
What?
A is paired with 2.
Oh, yes, thank you. You're allowed to have repetition in the set, but this is a bijection, so A has to be paired with 2, so I could have an A paired with the second 2 here, but that would actually be the same as this because 2 is being paired with only A. It just happens that A is in there twice. So that's the concept of a bijection. From the concept of a bijection, we can come up with the concept of cardinality, which is a measure of the size of a set. So we start with the set 1, 2, ... n. So this is a finite number set, it has a finite number of elements. These are all natural numbers. We define this as having a cardinality n, and any other set that has a cardinality n, we can create a bijection between that set and this set. I'm not going to prove that, but that's a pretty easy proof. So that's for a cardinality of finite sets. We can extend the concept of cardinalities into infinite sets. So if I were to just erase the comma and the n, this would be the set of all natural numbers, and that is an infinite set that we have just defined the cardinality aleph naught. Aleph being the first letter of the Hebrew alphabet, we just use that to denote an aleph looks kind of like a wonky N. It's the best way to describe it. Kind of like that. It's the best I can draw it. So we just define the cardinality of the natural numbers being aleph naught. So if we can create a bijection between one infinite set and the set of natural numbers, we can show that the cardinality is A left knot, so I'm gonna do that right now. So let's take the set of natural numbers and the set of whole numbers, which is just like the set of natural numbers, but we start counting at 0 instead. So for this set, we can just map, this is the natural numbers, and this is the whole numbers, which doesn't have a special letter, it's just called the whole numbers. We can take the element n minus 1 and map it to the element in n, like this. So 0 in the whole numbers gets mapped to 1, 1 in the whole numbers gets mapped to 2 in the natural numbers, and so on. And that is a bijection between the two. So we have shown that the natural numbers and the whole numbers have the same size. For the next one I'm going to show is, instead I am going to do the set of integers, z. So that is the set -3, -2, -1, 0, 1, 2. So this is the set of all integers, z. Now, it may seem like these are actually different sizes because it goes from -infinity to +infinity, but instead of writing it out like this, I'm just going to reorder the set as 0, -1, 1, -2, 2, -3, 3, and so on. So from this reordering, it is clear that I'm still going to get every number in z when I reorder it like this, but it also allows me to create a bijection. So 0 goes to 1, -1 goes to 2, 1 goes to 3, -2 goes to 4, and so on. So this is a valid bijection between these two. So n and z, the natural numbers and the integers, have natural numbers and the integers have the same cardinality, being A left knot. The next one, it has a lot of people have trouble comprehending sometimes. It's showing that the set of rationals and the set of natural numbers have the same cardinality. So to do this, the set of all rationals is the set of all numbers that can be written as one integer over another integer. So the way I'm going to write this out is instead of writing them out in a set like this, I'm going to write them out sort of as a matrix, like this: 1 over 1, 1 over 2, 1 over 3, 1 over 4, and then 2 over 1, 3 over 1, 4 over 1. And so the numerator is dependent upon the row and the denominator is dependent upon the column. And it's pretty obvious that all the natural numbers are going to be taken into account. Oh, and I guess yeah, I forgot the zeros, so that'd be 0 over 1, 0 over 2. Yeah, so it should be obvious that all the rationals are taken into account. So instead of just trying to list them instead of trying to create a bijection like this, I can count them going diagonally like this. So I pair like that. The 2 I pair with 1 over 1. The 3 I pair with 0 over 2. The 4 I pair with 2 over 1, and so on. And this contains all the rationals, and I'm creating an arrow from from the rationals to the natural numbers. This proof doesn't actually show that they have the same cardinality. What it shows is that the rationals can have a cardinality can have a bijection with a subset of the natural numbers, because if you look, anything along, oops, this diagonal, 1 over 1, 2 over 2, 3 over 3, those are all 1, and those will be mapped to different elements. Well, something else I can do, and so this makes it seem like there are more natural numbers than rationals. Something else I can do is instead try mapping n to 1 over n, and then if I just do this for all the natural numbers, and I think about numbers like 2 over 3, that's not mapped to any natural number. So I've shown that the rationals have a bijection with a subset of n, and n has a bijection with a subset of q. So the only way for both of those to be true would be for n and q to have a bijection between them. And there is a way to do it using, what's it called? It's called a Stern-Brokat sequence, or a Stern-Brokat tree. I'm not going to go into that, but that is a way of creating the bijection between the two. Okay, and then the final proof on cardinality is one that comes from Cantor, and it's a few hundred years old. It's pretty famous. It's called his diagonalization argument. I'll just go through it and then I'll explain the results afterwards. So to do this, I'm gonna pair off my natural numbers, or I'm gonna write them increasing down this way. So I'm creating a bijection between natural numbers and then what are going to be the real numbers here. So every real number, if you has a infinite decimal expansion, you can always just, if it's like 0.5, you can always just tack on an infinite number of zeros. So so I'm just going to start pairing off random reals with natural numbers. So like this one will just be 0.5, 0, 0, 0, 0, 0, 0, 0, and so on. This one will be like 0.1, 2, 3, 4, 5, 6, 7, 8, and so on. And I can just do the same thing. Well, it's not going to be the reals, it's specifically going to be numbers between 0 and 1. And then 4, 7, 3, 2, 8, and so on. Well, I can do this for every natural number, but I can always take a new number, or I can always construct a new number that's not in this sequence by taking the first digit from the 1 paired with 1, and if it's 0 through 8, I will shift it to be, I will just add 1 to that digit to make it 1 through 9, or if it's 9, I'll just make it a 0. So in this case, 5 becomes 6, 2 becomes 3, 5 becomes 6, 7 becomes 8, and so on. Now, I will always have a rational that's not in this list, or I will always have a real number that is not created, or that is not in this bijection, or that is not in this list. So I cannot create a bijection between the naturals and the reals. What this means is there are more real numbers between 0 and 1. Than there are natural numbers. So the point of this proof is showing that there are different sizes of infinity. It's a pretty easy proof to show that, we state that this size is, instead of this one having a left naught, we state this one has a left 1, or size of a left 1, and there's an easy way to show it using power sets that a left 1 is equal to 2 to the a left naught. So I'll let you guys do that as for fun. So yeah, those are some interesting things about sets. But I guess talking about spaces now. This idea of the different sizes of infinities will come back at the end of the lecture. But for now, I'm going to move on to more vectors for a bit. Before I do, I need to talk about another definition of spaces. Space is a set with extra restrictions, or a non-empty set with extra restrictions. An example is a metric space, which is a set and a function called your distance function, which tells you the distance between two elements in the set. And the distance function has 4 axioms it must satisfy. And so yeah. So in your intro sequence linear algebra class, you've probably been told that a vector is either a distance and a magnitude, or you can think of it as an arrow. While technically those are correct, they are very limiting to think about vectors as that. Instead, the better way to understand vectors is to talk about vector spaces, specifically abstract vector spaces. An abstract vector space is a non-empty set which satisfies the following 10 axioms. So for a vector space V, it must have, so we'll call our vector space V and we'll call the elements in it X and Y. The first axiom is that X plus Y has to equal Y plus X. So it's commutative under addition. It is commutative under addition. X plus Y has to be contained in V, so it's closed under addition. If I have any scalar alpha, which is a real number, well, to be more general, it's a complex number. Just to make it more general, it also works if I put in the restriction of real numbers. Alpha x has to be contained in V. And let Z also be an element in V. Then X plus Y plus Z is equal to X plus Y plus Z. So addition is associative. 5. There exists an element called 0 in V such that 0 plus X is equal to X. So there's an additive identity. There exists a negative X such that X plus negative X equals 0. 7. If I have AB times X, where A and B are scalars, I'll write that out. If A and B are scalars, then AB times X is equal to A times BX. So scalar multiplication is associative. A times X plus Y is equal to AX plus BY. So scalar multiplication is distributive among, or is distributive along vector addition. A plus B quantity times X is equal to AX plus BX. So scalar multiplication is distributive along scalar addition. And then 10. There exists a scalar which we call 1, such that 1 times X is equal to X.
Okay. Bro, you got hypo on number 8.
Oh, yes, that should be X. Thank you.
And it should be A.
Oh, no, you're right. That should be AY. Yeah, so these are the 10 axioms. If you can prove a set satisfies the 10 axioms, it is a vector space, and so its elements are vectors. Example of vector spaces are the classic one you study in your inter-sequence linear algebra class, Rn, except they always tell you it's n greater than or equal to 2, but also the real numbers all satisfy these axioms. The set of n tuples of complex numbers. The set of all functions that map R to R also satisfy all these axioms, and I'm going to talk a little bit more about that after I talk about an inner product. The set of polynomials of degree n, or degree less than or equal to n, also satisfy all these axioms. Most likely you understand what this n means, but just to clarify it, that's something called a Cartesian product, where if I have two sets, A and B, their Cartesian product written out like this. Is this on camera? Sorry. Yeah. Their Cartesian product, A times B, is an ordered pair, where the first element is an element of A, and the second element is an element, or the first part of the Cartesian product is an element of A, the second part of the ordered pair is an element of B. This is the Cartesian product of two sets, but I can then take this Cartesian product and take the Cartesian product of the second set. So I now have a 3-tuple. And again, A is an element of A, B is an element of B, C is an element of C. And so that's what I mean here when I say Pn, Cn, Rn. Okay. The concept of span is pretty simple. Basically what span is I have a set of vectors and all in the same vector space. And the span is any vector, or is the set of all vectors that I can write as a linear combination of my given vectors. So I'm just going to do it for the set of two vectors, but it generalizes easily to a set of n vectors. So if I have v1 and v2 both in a vector space V, the span of these two vectors can be written as alpha1 v1 plus alpha2 v2. Any vector that can be written like this is in the span of v1 and v2. Your set, and a set of vectors is linearly independent if this equation implies alpha1 and alpha2 equal to 0, or equal to 0. That is useful when we're talking about projections, which I'm going to do right after I talk about inner products. So, in your inter-sequence linear algebra class, you guys would have talked about a dot product, which is, or also called the scalar product. That only works for vectors in Rn. There's a generalization of that called your inner product of two vectors, which I'm going to write out as like this, which is the inner product of x and y. An inner product, an inner product space is a subset of all vector spaces. It's just a vector space that has 4 more axioms in addition to the previous 10. So the first axiom, it first states that there's this function, the inner product, and the inner product has to satisfy these 4 axioms. That is, and this inner product maps V, so it takes 2 elements from V, so that's why this is V cross V, and it maps it to either R or C. I'm just going to write the most general case for the inner product being mapped to C, but these all work also for if it's mapped to R. So the inner product of x and y has to be equal to the conjugate of the inner product of y and x. What this means is if the conjugate of a real number is itself the conjugate of a negative, or not a negative, of an imaginary number is the negative of itself, and the conjugate of a complex number is the real part minus its negative part. So, I mean, that's something you guys should have talked about when you guys were talking about conjugates with your in your calculus classes, and that's what this bar over the inner product means. Linearity, so x plus y of z. So the inner product of the quantity x plus y with z is the inner product of x with z plus the inner product of y with z. You have positivity, which states that the inner product of any vector with itself has to be greater than and or equal to 0, with equality holding only if equality only holding if x is 0. And then for associativity, which states that where a is a scalar, x and y are vectors, this is just equal to a times, basically if it's in the first component, I can just pull out a scalar. If it's in the second component, I first apply this rule to get it into the first component, pull it out, and then reapply this rule to switch it back. So you would find that if it's in the second component, this becomes its conjugate. Okay. Yeah, I'm gonna skip that and, right, orthogonality. So I have two vectors. They are orthogonal if their inner product is 0. That is almost exactly what you were told in your linear algebra class, except there's one difference. The same vector space can have multiple different inner products. So the normal dot product of like x1, y1 plus x2, y2, that's the normal Euclidean dot product. I could just as easily say 2 times x1, y1 plus x2, y2, and that works just as well as a valid dot product, or that valid inner product. And in this case, any vector, so I could have vectors that are orthogonal with the first inner product that are not orthogonal with the second inner product. Yeah. So if I have a set of orthogonal vectors, so I have a set of orthogonal vectors which I'm going to label E sub I. I can take the vector x and I can rewrite it as the sum of, or the sum over all I So what this allows me to do is allows me to, and because these are all orthogonal vectors, what this formula is basically saying is this is what's called the projection operator for E sub I. You can sort of go back to the picture you got in your intro sequence linear algebra class, which is if you have two vectors, then it would be like the shadow of one vector on another, but that only works for the original, or for the dot product. The same idea holds with the generalized inner product, but it doesn't work so nicely with pictures. So, another thing is that you can use, so if I'm given x and say, and a set of, like the EI bases, I can then take, so EI is a set of bases, and let's call FI another set of vectors that span the same span the same set as the EIs, so they're both basis for the same set. This is also equal to this would be a so because this is true, I can use this formula to change my basis from, so like the example that you will see in your not in your differential equation class, in upper level physics classes or electrical engineering classes or CS classes, is something called your Fourier transform, which is denoted by f hat of your f hat of omega is equal to the integral from 0 to infinity of, and it's e, what is it? 2 pi I t, yes, dt. I can't remember if there's a negative or not here. I don't think there is. There will be an annotation in the video that will say whether or not there's a negative there. So what this does is, if you have a function as a function of time, this function lets you represent it as a function of sinusoidal waves of different angular frequency, because the set of sines, so like sine of t, sine of 2t, sine of 3t, sine of 3.5t, and so on. All of these are orthogonal functions with the with multiple inner products being an integral. So like the inner product of two functions, f and g, is an integral of f of x times g of x, and on certain bounds, but any bound, if the bounds encompass an integer number of periods, then these functions are orthogonal. So this is the same idea as this formula, except because I now have an infinite number of bases, I have to replace my sum with an integral. So the Fourier transform is just an application of linear algebra of changing your basis, or just using projection operations. And that's something they never teach you in physics or CS or electrical engineering classes, that make this like random thing they throw at you make a lot more sense. And yeah. So another cool example of this formula is there are something called the Legendre polynomials. The Legendre polynomials are a set of orthogonal polynomials on the interval -1 to 1, which means if I take their inner product, as I had written out right here, or I guess in the terminology of the Legendre polynomials, so p sub n of x and p sub m of x, these are both Legendre polynomials. That's equal to the integral from -1 to 1 of if n, it's equal to 0 if n is equal or not equal to m, and it's equal to L, or not L, n over 2, I want to say, if n is equal to m. So these are really useful because these are polynomials. So from that, what we can do is we can take a function, just a general function f, and take its inner product, and apply this formula, and we can get a power series representation because the Legendre polynomial, p sub n of x can be written as 1 over 2 to the n factorial. Minus 1 or plus minus 1? So this is the function for the nth Legendre polynomial, or the nth degree Legendre polynomial. So applying this function, or applying this operation, but truncating the number of terms instead of going across all infinitely many Legendre polynomials, only doing a finite amount of them, we can get a power series approximation to this, or to a function f. So we can do that, and from that you can actually derive a Taylor series if you by manipulating or if you, instead of truncating it, use the infinite series and massage it a bit, you can actually derive the formula for the Taylor series. But just by truncating it, you can actually get a pretty good approximation, or nth degree approximation of a function. So the final thing I'm going to talk about are something called transcendental numbers. So before I was talking about the set Q, which is the set of rational numbers. Rational numbers are any number that can be written as the ratio of two integers. Transcendental numbers are sort of like irrational numbers, except a little more complicated. You have a polynomial, so like axn plus dx plus dot dot or cn xn plus cn minus 1 x to the n minus 1 dot 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 plus c0 is equal to 0. A algebraic number is a root to this is the root of a polynomial in this form with all the coefficients being integers. A transcendental number cannot be written as the root of some polynomial with purely integer coefficients. So, using what I talked about before, of cardinalities, we can actually prove that transcendental numbers exist. In general, it's very hard to show a number is transcendental, but it's very easy to prove that they exist. So, if you remember before, my proof of that Q, or part of my proof that Q had the same cardinality as N, was I wrote the rationals instead of as a line, or instead of in one line, I wrote them in a square array. Well, if you, any polynomial with integer coefficients can be represented as a vector in Zn, where n is the degree of the polynomial and the coefficients are each component of this vector. And in a similar way, I can do instead of just like trying to count across a row, I can do some wonky, because in like the Z3 case, there will also be dots coming out of the board. In the Z4 case, I can't help you guys picture it. And Z5, don't get me started talking about that. They're trying to have me explain that. You can always do, instead of doing the diagonal lines like we did for like the case of Q, you can always do some spiral case. So it's like you go, for the case of Z3, you would go like down, right, up, out, down, out, down, left, up, out, what is it? It's, you start here, then you go here, 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 and so on. So you can always create some wonky path where that would allow you to biject all of these to n. That is true because this is a countably infinite set. Or that's what it means to be countably infinite. It means your cardinality is Aleph naught. That's another term instead of Aleph naught. A lot of people say countably infinite or listably infinite. Because Zn is countably infinite, we can create the bijection with n. We cannot do that with the general set of polynomials Pn, because that has a bijection with Rn, not Zn. So what that means is there are that Zn is a proper subset of Pn. And so by proper subset, I mean Zn is contained in Pn, but there are elements in Pn that are not in Zn. Now, Zn will have, or each vector in Zn will have at most n roots. Well, it will have n roots up to multiplicity. So like it could be something like x minus 1 to the n. So it has n roots, but they're all x equals 1. And so if we take all of the elements in Zn and like just create a new set that is Zn but copied over n times, we can still create a bijection between that and Zn. So that will still be a proper set of Pn. So that means that the set of all roots of these polynomials is a proper subset of the set of all roots of these polynomials. Which means there do exist numbers that cannot be written, or that cannot be written as the root of some polynomial of just integer coefficients. But we just proved that transcendental numbers exist. Some examples of transcendental numbers are e, the basic natural logarithm. That is fairly difficult to show as transcendental. Pi, which was after transcendental numbers were first introduced. I think it was about 50 years before pi was shown to be transcendental. So that was really difficult to show. If I start writing out 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I just start writing out every natural number in order. That is a transcendental number. The sum of 10 to the negative k factorial. So this will be a number that is mostly zeros in its decimal expansion, but in that would be 2, 1, 0, or I guess let's set that n equals 1 to infinity. That's 1, 1, 0, because 1 is 0 factorial and 1 factorial. So that becomes a 1. 2 is 2 factorial. 3 factorial is 6. So first place is 1, or first place, second place, third place, fourth place, fifth place, sixth place becomes a 1 because it's 3 factorial. And so on. So I just continue that out. That is a transcendental number. Numbers that are not transcendental are I, because that is the root of x squared plus 1 equals 0, and 1 and 1 are integer coefficients. square root of 2, or the square root, or the nth root of any real number. No, the nth root of any rational number. Because just the square root as the obvious example, I can take, for the example for square root 2, I can write x squared minus 2 equals 0. For the root of any rational number, p over q, I can always say that would be q x squared minus p equals 0, and because this is a rational number, p and q are integers, so q and p are integers here. So, yeah. And that's my talk. Any questions? Yeah.
Questions?
Yes.
When you say that the inner product space is a subspace of a vector space, do you mean that
It's
there are
it's a subset of all possible vector spaces. So there do exist vector spaces that don't have inner product spaces. Or, I guess the best idea to put it is with a Venn diagram. So this is the set of all possible sets. Okay? Now, no, I'm not gonna do the barber joke. So, sets. This is the set of all topological spaces. This is the set of all metric spaces. This is the set of all vector spaces. This is the set of all inner product spaces. Okay?
what's the topological space?
Topological space is a set with certain properties. I forget what the properties are for a topological space. This is just the picture Wikipedia had. So, yeah. Yeah, there exist vector spaces, because I can construct vector spaces without, like, Rn. I don't have to associate a inner product with that. So that would be a vector space without an inner product. But I could associate the dot product with that, in which case that now becomes an inner product space.
So if you want to find all the inner product spaces associated with a vector space, how do you go about doing that if you know that there are
You
multiple?
don't, because there are infinitely many. Because there are infinitely many choices for my inner product. Because I could do the normal dot product. I could take the normal dot product and just slap on any coefficient I want. And then I could start including cross terms like A2, V7, or whatever. So I can start adding any cross term I want. And all of those would still form valid inner products. So, I mean, I can always just say this set R is the set of all vector spaces. That's not really useful, but that is that set. So I can always like write down the set, but there are no useful properties of like the set of all vector spaces or the set of all inner product spaces. Does that make sense?
Yeah.
Any other questions?